Alright, hello. So for today's notes, you should have a blank piece of paper out, a little bit of notes on that first, and then you should also have a sheet that looks like this. It's a little half sheet, so I'll get to that in a second. We'll start with your own notes. So this is Unit 7, Day 3. And you can just call this More Examples with Limits. Okay, so we've been doing limits for a few days now. You've seen them graphically, numerically with a table, and algebraically by plugging in points and doing some algebra with it. So at this point, I'm not going to specify what you have to do. I'm just going to say use the most efficient method. To determine each limit. And the first one we're going to do is the limit as x approaches 2 of radical x plus 2 minus 2 all over x minus 2. Okay, so we've kind of talked about these types of questions a little bit yesterday. The first thing that you should always do when you're finding a limit is what? You should plug in the value. If you get anything other than that indeterminate form, which is 0 over 0, you're done, and we have our limit. Okay, so let's see what happens. If I plug in 2, this would equal radical 2 plus 2 minus 2 all over 2 minus 2. So that's radical 4, which is 2, minus 2 is 0. All over 2 minus 2 is also 0. That's that indeterminate form. And that means we have to do more work. Because we could have a limit that doesn't exist. We could have a limit that goes to infinity. We could have a limit that approaches a specific value. We just don't know right now. Okay, so now it's up to you what you use. You can use a graph if you want to use a graph. You can use algebra, but at this point, the only algebra you really know how to do is factoring, and there's not really any factoring that's going to happen here, so algebra is not probably going to be the way to go, although there is an algebraic way to do this that we're going to talk about in a couple of days. So it's kind of down to either you're going to have to use a graph or you're going to have to use a table. And on your first quiz next week, this is what this is going to look like. You're just going to have to come up with a way to do it. So I prefer the table. I think that just shows the limit a little bit better. So since the limit as x approaches 2, what would be a good first x value to start with? Something like 1.9. And then you want to get closer, so 1.99. Remember I told you have to show at least 2 on either side. Sometimes it helps, if you're really not sure what the limit is, to show a couple more just to see a trend. So I'm going to go 1.999 also. 2.001, 2.01, 2.1. So you want to go a little bit both ways. And then go to your calculator, and hopefully your table's still set on ask, but if it's not, make sure you go to second table set that up on ask like we've been doing. Throw this into y equals, it's a fraction, so we need parentheses. So we'll do radical x plus 2 minus 2, all divided by x minus 2. And then I'm going to go over to the table, plug in these values. So we want to do 1.9, 1.99, 1.999, and going the other way, 2.001, 2.01, and 2.1. Then just looking at your y values, you can see I'm definitely approaching what looks like I'm kind of sandwiching in on a certain value. So it looks like the limit definitely exists because it goes to the same thing from the left and the right. And if you had to guess what you think it's going to, what does it look like the limit is? hopefully you're saying approximately 0.25, which would be 1/4. And it turns out that that is the limit of this expression. It is 1/4. It can be proved algebraically, and again, I'll show you how to do that in a couple days. So if you're showing me work on a test or something, you basically just need to copy down this table and show me what happens here. So copying that down, we've got 0.25158, 0.25016, 0.25002, and on the other side, we've got that 0.24998, and then we've got 0.24984 and 0.24846. So that'd be the kind of work I'm looking to see, and then you can show as you're approaching 2, the limit is approximately 0.25. So we'd say for my answer, the limit as x goes to 2 of radical x plus 2 minus 2 all over x minus 2 is 0.25, or you could say 1/4. Okay, and that's really the best notation. You really should write out limit every time, just so that it's clear what you're saying the answer is. Okay, so that's what you have to do if there's indeterminate form. Once you plug it in, use some other method to determine the limit. And let's do one more. Second one is the limit as x approaches 0 of 4 over tangent of 3x. Okay, so when I see this, I'm already pretty happy because I know for sure it can't be indeterminate form, because when I plug in whatever number, the top's always going to be 4, so it's definitely not going to be 0 over 0. Remember, you want to be in radian mode anytime you're dealing with real numbers and limits here for trig functions, so we'll make sure we're in radians. But we'll plug in 0, so it's going to be 4 over tangent of 3 times 0, which is tangent of 0. And hopefully you know what tangent of 0 is. If you don't, you'll have your calculator. So again, mode needs to be radian, and you can see that tangent of 0 is 0. No big surprise. So that's 4 over 0. So that's not indeterminate form. It is undefined. So what's that mean? It means the limit does not exist. Okay, so if you want to write it out in notation, the limit as x approaches 0 of 4 over tangent of 3x does not exist. Now next year in calculus, we might delve a little bit further into seeing just how it doesn't exist, because maybe it's a limit that goes to infinity, maybe it's a limit that goes to negative infinity. We could check the graph or a table to kind of confirm that. But for this year, just saying the limit doesn't exist, we'll stick with those. Okay, so flip over to that half sheet, because I also want to talk about piecewise limits again. Now, we've done these a little bit the last couple days also, but these can be tricky for people. So there's 2 ways to solve these piecewise limits that I'm going to tell you this year at least. We can try to solve them graphically, which is a little more visual, but it's a little more annoying to actually do, or we can do algebraically. Okay, so if I'm solving one of these graphically, let's make a table on here. And make some axes. Okay, I need to graph each of these. So if I want to graph x squared minus 2, make a little table up here. This is y equals x squared minus 2. Remember the values we're allowed to use. X values have to be less than 0. So we need to pick 0, but remember that's going to be an open circle. I'm going to have to go -1, -2, dot, dot, dot. I plug in 0. 0 squared minus 2 is -2. I plug in -1. -1 squared is 1. And 1 minus 2 is -1. If I plug in -2, -2 squared is 4. 4 minus 2 is 2. And we know the shape is going to be, since it's an x squared, it's going to be a parabola. Okay, so 0, -2. And again, it has to be an open circle. And then -1, -1, -2, 2. It's going to look something like this. Now between 0 and 1, it's just negative 2. There's not really a lot to show for a table there, if you really want to. 0, which is going to be a closed circle because it's less than or equal to, is negative 2. And 1, which is going to be an open circle, is also negative 2. So that means this gets filled in here. And then over to 1, which is an open circle. Sorry, it's a little hard to show it here, not a lot of room. Let's see if I can do a little better with that. So this is filled in. And then this is an open circle. And that is connected in between there. Okay, and then the last one's going to be a line. This is y equals x plus 3. 1 can be a closed circle. We're going to do 2, 3, etc. So if I plug in 1, 1 plus 3 is 4. Plug in 2, 2 plus 3 is 5. Plug in 3, 3 plus 3 is 6. So we've got 1, 4. So we've got a jump there. 2, 5, 3, 6. And as I shoot off that way, the graph's going to look like that. Okay, so now I'm ready to find these limits. So the limit as x goes to 0, negative means 0 from the left. So as I come in from this side towards 0, what value is the graph approaching? Hopefully you're saying negative 2. 0 from the right means I'm coming in from this side. And there I am down there, also approaching negative 2. Since the left hand and right hand limits are the same, we know the limit as x goes to 0 is also negative 2. And f of 0 is where the function is defined. When x is 0, y is negative 2. So all of those are negative 2. On the other side, as I go to 1, so going to 1, switch over to a different color here. 1 from the left would be coming into 1 from this way. And that's when I'm down here on the graph. So that's still negative 2. But coming into 1 from the right, the graph's up here on the right of 1, and that's going to a value of 4. So since the left hand and right hand limits are different, we'd have to say the limit as x goes to 1 does not exist. But f of 1 exists. F of 1 is where the dot is. That's right up here. So f of 1 is 4. Okay, so graphically, you'd have to be good at sketching out a piecewise function, but then hopefully you've had a lot of practice with that. Coming up with the limit shouldn't be too bad. Now remember, I told you a minute ago, the easiest way to find a limit is just to plug it in. So you can do that also. If I don't use a graph, I can find it algebraically. We just have to be smart. If I'm first looking for the limit as x goes to 0, negative, that means I'm plugging in values technically not at 0, but to the left of 0. So I'd be plugging in like x equals negative 0.1 or x equals negative 0.01. So which of these three domains does negative 0.1, negative 0.01, etc. fall into? It falls into this one. So if I plug that limit of 0 into this first equation, this just tells me I should be looking at values to the left of 0. That means this is the equation I use. Now plug 0 in. I mean, you could use a table, but I could just also plug in 0 as long as it's not indeterminate form. So I would plug in 0 squared minus 2, and we'd get minus 2. 0 from the right, you're thinking of plugging in values like 0.1, 0.01, 0.001. Those are all values in this domain. So that value is just the equation negative 2. So the answer is negative 2. To get the actual limit as x goes to 0, since it's still split left and right, you have to look at your left hand and right hand limits. And again, since they're the same, it's negative 2. And then f of 0, this is your actual x value you're plugging in. So the domain that 0 falls into is this middle one, and your answer is negative 2. Over here is x goes to 1 from the left. So again, 1 from the left, we're using numbers like, if I was making a table, 0.9, 0.99, 0.999. That's using this domain, the middle one here, 0.9, 0.999, etc. So if I plug in 1 into the first equation, again, there's nothing really to plug in, you get negative 2. 1 from the right, you'd be plugging in numbers like 1.01, 1.001, things like that. Now you fall into this last domain, so you're using the third equation. So plug 1 into that, and again, as long as it's not indeterminate form, we're good. So that's 4. Since 1 is split between two domains, we'd have to look at left-hand, right-hand limit to determine is that limit as x goes to 1. Since they're different, does not exist. And finally, f of 1, again, now we're actually plugging in a value of 1. That falls into this last domain. Plug 1 in. Again, you get 1 plus 3, so the answer here is 4. Now, if you look at both of those, obviously you get the exact same answers. You should, because it's just two ways to identify the same limits. So on your test next week, when I give you a piecewise graph like this, it says it's going to give you the option to do it graphically, but if you'd rather do it algebraically, that's fine too. I'm not going to specify which one you have to do. So if you understand the algebraic method, I think that's maybe a little bit quicker. If you prefer the graphic method just to look at it visually, you can do that way too. Okay, that's all we got for today. So there's a homework worksheet, mostly graphically. There's an algebraic one at the very end without a graph that you can plug in like we just did. If there's time left over, get started on that. Otherwise, have a good day, and I will see you tomorrow.